Can you turn on the lights? Yeah? Okay. The video is on? Yeah. Okay. So good. You have to share the screen. Did you share the screen? Yes.
Also, yeah. Should be okay, yeah.
Okay. Yeah, it's good. Okay, you can start.
Okay, thank you. Welcome back, everyone. I hope you had some nice discussions and refreshments in the break. We now kind of have 1 hour to talk about the KISTE project, which is kind of running for 1.5 years already, and I'll provide you some context, what we do in the KISTE project and what the team looks like, and also kind of what's all about. And we also need kind of some input from you. So we have kind of small survey in between. So kind of the overall challenge or aim of the KISTE project is really to kind of to bridge the gap between domain knowledge and infrastructure. So what we've seen kind of, well, for the project proposal, that many researchers like you have very good ideas what to do with machine learning and analysis of Earth system data. But at some point, it's very hard to get this applications, this kind of scripts that you write onto the infrastructure and have it kind of computing for larger areas of interest or for longer time spans. So that was one ambition of the KISTE project, to bridge actually this gap. So to make life easier for researchers to really use AI for the Earth system analysis that they would like to do. We have a couple of partners. Forschungszentrum Jülich, Martin, Scarlett, and Ankit are here present in the audience. Then University of Cologne, where nobody could join if I didn't overlook someone. RWTH Aachen is one partner as well. University of Bonn, Ribana will talk on Thursday, give a session here. And then we have Ambrosius, GmbH, Markus and Thomas. Thomas here will kind of join me for the second half, and Markus you got to know this morning. And then 50 to North, so we will have Christian who's going to join tomorrow. We have Markus, Johannes, and Martin already here, and myself. And obviously, as you see, we are co-hosting the summer school this year because we thought that kind of the KISTE project and the KISTE theme kind of nicely fit to the OpenGeoHub setup and the kind of long series of summer schools that Thomas Love has been preparing over the past years. So setting the scene, and of course important, it's funded by the Federal Ministry of Environment, Nature Conservation, Nuclear Safety and Consumer Protection, as it's kind of named recently. Yeah, so what we have more kind of content-wise, not just kind of formal-wise, we would like to have access across different data providers to drive AI applications. We would like to support different analytical infrastructures, so we would like to provide a system that you can use and kind of prototype in the local machine. You can distribute it to the cloud, but you can also use it in the high-performance computing cluster, which we use at the Forschungszentrum Jülich. And we have very different fields of applications, as you will see. So I kind of very briefly introduce the different PhD topics that we have within the KISTE project, hosted with different universities which are partnering. And kind of a different theme we're working on is kind of storage of trained models. So how can we store a model? How can we versionize a model? How can we kind of hand over models so that somebody else could use it afterwards? And the same story is kind of versioning of data and models. So we have to somehow kind of find versioning systems for data and embed this in our overall KISTE platform that we will see. And we'll also produce an e-learning platform for domain experts, meant as a massive open online course where we kind of produce the insights that we kind of get from our PhDs about the obstacles that they see that they have to use their AI ideas in kind of the infrastructure that you provide, and try kind of to make life easier for the domain experts to kind of to get to know machine learning and artificial intelligence applications for the Earth system data. That's kind of the aim of this massive open online course that we also develop during the KISTE project. And as next step, I will kind of have a kind of quick survey here, kind of talking about where the gaps and challenges. So where do you see the gaps and challenges if you think about your Earth system analysis you would like to do, and if you think about kind of how can I get this into kind of larger computing infrastructure, how can I kind of extend my study area from series of tiles, kind of larger regions going from country to continent-wise or global applications. So where do you see are the gaps and challenges? And what I try to do here is to provide an online survey. Which So I hope it should start. It's a survey. Here are the different questions that will kind of pop up during the survey. You can either scan the QR code or type in these URL down here. I could also post this over MetaMouse, I guess, right? MetaMouse is also...
It's also open in the other Firefox
window. The other Firefox window?
Yes.
And then you have here, where's Town Square? Here's Town Square. So if you're wondering about what hinders your application to really run on a larger area of interest. So if you think about your application, what would change if you have to, or what would you have to change to make it available? Can we go back to full screen? Yeah, good. And also kind of how reproducible is your code? It's kind of data available, or kind of the next steps, you have also scripts available, and how to kind of proceed there. How do you access the data? Which APIs do you use? What's your kind of storage region? Which data processing approaches, or kind of, I think it termed differently, what's your kind of favorite, your most important data pre-processing step, and also your most important data modeling approach? So just kind of not putting the long story, just kind of what's your favorite there, the most used one. And also towards kind of how modelize your application. So do you use many models or modules in your application? Or have you just kind of different pre-processing, analysis, and results sections? So can you kind of rebuild this and kind of cascade this program? Or maybe kind of build different trees around your modular applications? That's one thing we're wandering around, and that we're kind of thinking about whether this is a useful feature for the AI application platform. And this goes along with the kind of use multi-step workflows. And kind of final question, which is kind of a very easy one, do you use containerized solutions? Does this work? Can you fill in answers directly, or do I have to change something on the...
It works.
It works. That's good.
In my case, it says participant limit exceeded.
Participant limit exceeded. Okay.
I left, so you can get my spots.
Seems like I didn't read the fine print, how many participants can join at the same time. Sorry for that. Let me see. Okay, we see some results at least. We will keep that open. So I think we don't have time to kind of wait like 10, 15 minutes now to kind of until you fill this survey, which kind of turned out to be a longer survey than I initially thought it would be. So it'd be nice kind of to see very different word clouds here, what you see. So reproducibility, kind of data set, package version, dependencies. Yeah, okay, it's filling out. That's nice. No one is up to the main pre-processing step. So we're back on the questions up front here. Time. Yeah, time is a problem. I agree with that. To rerun the entire study and prepare this properly. Border structure, availability. Okay. I hope that we can still have more feedback once kind of somebody drops out of the session, and this is not kind of an once counted study closed limit. Sorry for not checking on that. While you kind of fill in some more answers if you like and can, I would just kind of continue the presentation so that we don't lose any time here. But it's kind of also valuable input for us, also for the KISTE project. So it's not just kind of fun exercise, but it's really something that we kind of reuse afterwards, and we'll also kind of bring up and maybe have a chance, another session, maybe on Friday, I don't know, to kind of quickly show these results to reflect on your answers here. So then I kind of jump into the KISTE use cases. So I kind of I didn't prepare the content-wise. I just kind of collected all the different slides, and I also didn't do the studies myself. I'm not co-supervising it, so I'm just kind of trying to kind of collect them and present them here. Put the names up front and the university and the related people. So if you have any detailed question, I can connect you to the corresponding people for those different use cases. So first use case is wilderness by Timo Sturmberg from the University of Bonn, who's kind of working with a so-called Anthroprotect data set, which is also freely available on the website. And what he's trying to do is going to fit a model and to analyze where you can find the true wilderness. So true wilderness in Fennoscandium, that's what we can see here on this map. And here's kind of training data sets where you have protected areas and you have anthropogenic areas. So kind of where you see some examples where you see some infrastructure, and now you would like to kind of identify and classify based on the remote sensing images, what is true wilderness and how do these also kind of develop over time if you look at different wilderness areas. And the approach he takes is kind of from the field of explainable machine learning. So the activation space occlusion sensitivity. How this works, you kind of have this typical convolutional neural network setup that you might recognize, and then you kind of start to hide different features on your training data set. So it's like I take out the roads, and then I would like to know, okay, how does this change on the activation space? So which features are missing? And based on this kind of analysis, based on kind of including different parts of the study area and different regions and different properties, you start to understand what kind of is the sensitivity of my model to this approach. And then you can kind of repeat it for many tiles, look at different setups, different settings, and you get kind of nice maps of kind of what are the activation functions here. And you start to understand which features kind of are identified as anthropogenic areas or wilderness areas. And then kind of compare these nice plots here. So this is an example of a power plant where you see kind of clearly infrastructure here around the river. What's a bit open is kind of an open area, an open sea, is a wilderness, not in this case. It's an artificial lake, so could be seen as anthropogenic, but kind of other lakes might be just kind of wilderness and natural areas as well. And you kind of get a classification of where you find wilderness in this image, and where you find anthropogenic effects of the study. That's already the first use case. Some circles. And the second one is biogenic emissions, kind of the overarching theme. By Ankit is also here, so if you have any detailed questions, you can directly approach him in the next break to discuss what's going on in his PhD topic. And the question here is kind of doing the self-supervised learning, the constructive self-supervised learning approach. And you see that machine learning encodes kind of nonlinear relationships between inputs. Inputs can be anything, grid, cell, land cover images, and so forth, as you probably know. And the problem is often kind of lack of enough data, trained data, labeled data that you could use to build your relationships. So what you would like to do is really build it here self-supervised, and we start with transfer learning. So take a pre-trained model that has kind of certain features learned already, and that we can then kind of further educate, let's say, and further train for certain different purposes, but we kind of benefit from a large data set that we use here as a kind of pre-training data set, and then kind of continue this in this also kind of self-supervised manner. And therefore we look at contrastive learning. Yeah. So here is you take the image as a label itself. So here down is an image of a dog. And then you kind of start to take different views on this data set. You can crop it, you take subsets, you change colors, you change perspective, you go to grayscale and something. But all those different views on the same image should be the same, contain the same content semantically. So they all belong to the same class. So they are all labeled with this kind of image ID where you started from. And then you can kind of distort this image in very different ways and kind of train your model in a self-supervised way, so that you don't have to have this labeled data set up front, but you start with the kind of data set you have and derive the labels from that. What's currently done in this area is kind of you can do some Gaussian blurring, some color jittering. You can kind of horizontal or vertically flip the image. You can convert it to grayscale. There's some kind of way to generate different views of the same data set that you then can use in this learning approach. And what Ankit develops is kind of an alternative where you say, I also would like to introduce atmospheric transformation between different images, because this can also be extended to the non-visible layers that you could look at. So you can do it on multiple channels at the same time and generate even more views on the same image that you can then feed into your learning process to train your models that you would like to have. So he takes corrected and uncorrected images from the archives of Sentinel-2, kind of as a starting point, and uses these as inputs. And then he has kind of a corrected and uncorrected image, takes the difference between those, and then kind of randomly adds these differences to the corrected image. And then you can start to build kind of different views of the same image with different properties based on the atmospheric corrections. And as I said, you can do it on multiple channels at the same time, and then use this as input, as labeled input based on the corrected image for your training application. And or you have to, I don't know if you can see it on the beamer, hardly seeable, but there's a change from left to right where you kind of go from the uncorrected to the corrected image and slightly add up the differences that you have between the images based on these fractions here. And that's what's happening in the algorithm with a random number, and then use kind of for training of the models, which kind of outperforms in the study that he has done the current approaches that are available. This kind of lets us move to the third application already, which is hazard prediction by Anke van Edrich from the RWTH Aachen. And her topic is kind of shallow landslides. Here an example from Switzerland. And kind of, she's looking for kind of common geomorphological features of these different shallow landslides. And well, they're typically triggered by strong rainfall or snow melt events. And you can kind of move this data set or kind of collect this data set, collecting different properties of it. So for the covariates, she's looking to hydrology, land cover, topography, soil properties, meteorology, that you kind of all need to combine and gather the input data set, and then she feeds it to a random forest, producing hazard maps out of it, and wrong direction, gives a preliminary result, an example of a canton in Switzerland, where it kind of has a predicted landslide hazard for these different type of landslides. And one of her particular challenges was maybe to get to this data, which is kind of very kind of detailed and small scaled, and to build up all those covariates that are helpful to explain where shallow landslides might occur and where kind of decreased risk is of a shallow landslide. Then there's the next example. We're looking to numerical weather prediction models, sorted by KWF, working at the Forschungszentrum Jülich. And so we look at kind of powerful tools to simulate and predict. We would like to look into model uncertainties, and we hope to kind of improve the accuracy of the model-based data that we use at this point. And well, the problem is kind of observations aren't always accessible, and kind of while the models be projected to future, the observations typically you just kind of you don't have them for the future, of course. So we have to rely on historical present data. And the goal is that we can rely on historical relationships to kind of to extend that based on model-based and observation, and to extend these, and that we have correction methods to improve those variables obtained by the models, and especially when the observations are not available. So the data study and area is kind of Europe, and kind of split into different training periods over different years, so 16 years of training, then 4 years of validation, and 3 years here for the testing case. And what you see by this different approach, if you look at the different kind of histograms here for the actual predicted mismatches between, so there's an expected mismatch, of course, and between kind of the model and the observation and what the model produces, and then kind of correct this mismatch. And here's what you get kind of with this improved method. If you look at the actual predicted mismatches, and what he concludes is that you can improve here the root mean square error about 20%, correlation about 40% based on this approach. And yeah, so you get kind of with the corrected forecast model, you can yield further improvements in the hydrological applications, kind of then further downstream in the modeling chain to get a better assessment here. And also for further question, here's a contact email, but just kind of ask myself, ask me, and I can connect you if you like. Moving to another use case based on cloud variability by Draya Chatterjee from the University of Cologne. And you have the kind of, motivation, the cloud system kind of appearance structure is very diverse. So as you can see here, so very different patterns of clouds, very different shapes of clouds. and they have kind of an interest in cloud classification, so which type of clouds occurs in situations, and also in terms of, well, for instance, solar power production, with kind of our forecasts here. And well, you can use this kind of classification and this prediction of the cloud to kind of further understand the warming process and single source of uncertainty in climate prediction, so we can improve there and produce new machine learning-based approaches to better understand the role of clouds in our climate. So how the clouds are all organized, what is the cloud feedback that we have, the interactions, and how this interacts with the climate sensitivity that we see. And as briefly mentioned, clouds are kind of strong modulator of solar energy, of course. So kind of decide how much of this solar radiation can really kind of hit the solar panel. And so the solar variability has a strong impact on solar production. And the classification can help to kind of identify different regimes to kind of well, use in renewable energy production. What uses kind of satellite data as well for this study region here on different pixels, built up a machine learning approach, which I can't explain, but get in contact with him and he will explain. And kind of looking at an optimal clustering result, kind of for different clusters to look at, to kind of have different clusters of different cloud regimes and how they look like and how they might impact it. And kind of what he learned is kind of from larger areas, he could kind of transfer this to kind of from 2013 to 2015, but looking at small scale variations, small scale cluster separations, there's kind of no generalization currently possible, and you will need more training data to improve that. For the next use case, I would hand over to Thomas, who will also kind of give insights into the KISTE AI platform.
Sorry. Okay, great. Well, thank you, Ben, and thanks for your help. Sorry about the short delay. Yes, hi, I'm Thomas. I work in research and development at Ambrosis GmbH. But with the KISTE project, I actually have two roles. And yeah, luckily, these are research and development. So most of the time, I'm a software developer, and we are developing, as Ben already said, the AI platform for Ambrosis. But I am also a PhD candidate with Markus and Martin. And as such, I am my own beta tester for the AI platform. So I will use the opportunity of pitching my PhD research also as a motivation of why we are building this AI platform and as a first use case. You will see that I don't have any slides really. This is only partially due to laziness. More importantly, it is also to motivate and show you what we already have in well, a front end. So I will click around in my browser a lot. Hope that's okay. First of all, the title of my research project is Phase Transitions in Image Classification. Quite clear what I'm doing, right? Okay. So the title actually already suggests that there's two disciplines coming together. Image classification is a classic machine learning problem with a lot of applications also in the geoinformatics area. Phase transitions, then again, are usually the field of study of statistical physicists. So what we will be doing is using methods from statistical physics to understand some fundamental properties of image classification. As a motivation, we have written a small web app where we can actually play a game. The idea is we look at data sets in the presence of quite intense noise. So this image obviously is not usable for classification. I hope nobody from the audience really recognizes what's the ground truth behind this image. I mean, I don't need to motivate here why this is interesting. We've talked a lot about bad data and pre-processing. And what we are doing is basically we're trying to train models on such bad data, and obviously the models will not be better than guessing. But then as we reduce the noise, which you can see here, gradually, we have a quite rapid transition from no recognition at all to, well, optimal recognition. So this is the fashion MNIST data set. This is meant to be a stiletto. And typically, even with a simple perceptron on fashion MNIST, you would reach an accuracy of about 86%, maybe even up to 90%. This would be optimal in this case. And what we're interested in is actually this transition. So what is the critical amount of noise that a certain model can still somehow work with? As I said, we interpret this as a phase transition in a sense from statistical physics. So naturally, we have to do statistics over all these model runs. And as you can see here, don't try to understand this plot. I just want to show you how much data we have to deal with. So each of these points actually represents 10 runs already. So bookkeeping is one of my main goals here. And in the end, what we want to get, I can show you here a preliminary study. We have on the x-axis, if you will, the logarithm of the noise intensity, which is just a standard deviation of Gaussian white noise here. And then we have the logarithm of the data set size. So we can choose how much of the data we are actually using for training. And then we have the test score. The score here is just accuracy. And basically, we are interested in the shape of the surface we get here, because the surface can be described in terms of so-called critical exponents. There's a lot of theory on these critical exponents from statistical physics. And what we know from there is that these phase transitions are quite universal. So these critical exponents will not differ for a lot of model and data set combinations. And this we will use to categorize the data. So the application we have in mind here is that as soon as we know a model and a data set very well, we can switch out one of the two. So if we want to understand how a new model is behaving in terms of universality classes, we just use a data set that we know very well and compare the critical exponents, which you can compute from these surfaces, to the already known studies that we have made before, and then we know what the universality class is. From this, we can infer, for example, the scaling. We can say, typically in this class of models, we need this amount of data to have proper or near optimal performance of the model. Or if we do the other way around, we take a model, for example, a perceptron, with an unknown data set, we can use it to assess the quality of the data. So one of the main questions we are trying to answer here is how much pre-processing is enough, because it takes 60% of your time. So we want to cut this down as much as possible. So this as a pitch of my actual research. Now, the main challenges I already encountered in working in this is quite a few different fields. The problem is that it's hard to have a single source of truth for your experiments, because I'm dealing with data sets that I need to get somewhere. I mean, Fashion MNIST is just an S3 bucket provided by Zalando. So I need to make sure that this data set stays the same and is still available whenever I need to use it again. Then I need to track my experiments. So I need to have an idea of what did I do already and how can I use this in generating results. Then this is just the first steps. Of course, I will do much more post-processing of the data and much more analysis of the trained models. So ideally, I'm able to store my models as well. And then, of course, what you see here is just metrics generated from, in this case, 1,000 runs of model training. And I need to be bookkeeping all of this together. And ideally, I want to have one single source of truth for all of this details. And we actually couldn't find this before. And this is what motivates us to create the KISTE AI platform, which we are calling Mantik, which is Turkish for logic. So, well, and as a second incentive, actually, what Ben also already mentioned, all of the research projects in the KISTE project have access to the dual supercomputer at Jülich. And we did a survey there as well, and I tested it myself. It takes quite some time to learn how to use these computers properly. So the second incentive of creating this platform is also making life easier. With the platform, you will be able to just define some resources and don't need to know anything about supercomputers themselves and can just run it with a simple click of your mouse. I will show you what we have already with the platform, but it's a work in progress. This is actually a live preview. So there will be more coming every day now. Basically, the idea is that it's all browser-based. So you just have a website where you can just register or can have a free trial. Can also hit me up during the week anytime if you want to just test it, have a go at it, or know more about it. And basically, the main idea, the main point here are the projects. So a project is a collection of everything you need to recreate, for example, a paper that you found online. It should contain anything that is important for the reproducibility. So, sorry, wrong shortcut. If I go into one project here, I think I can enlarge it a bit. The idea is on the left, there's the entities that make up the project. So obviously there will be an overview, there will be individual runs. We'll come to them a bit in a second. But more importantly, we also include the code, so links to the GitHub repos, but also commit hashes that are mapped to the actual runs. So we can reproduce runs completely and not just say, yeah, it was this repo, but I don't know at which stage or what changes were introduced later on, maybe. Also, what is not already shown, because it's still work in progress, we will have an integration for a data versioning tool that will be integrated by 52 Degrees North. So that in the end, you will just have this website and you can click together. I have my code. I have some data set. They will work together. And you can just have a button here and run it on whatever infrastructure you like. So we are already supporting local execution on HPC, and we will soon be supporting also execution on the cloud. So this for the basics. Interestingly now, what really happens when you execute an experiment, this is what we call a single run, and this is integrated with MLflow. Does anybody of you know MLflow already or even use it? Okay, no one. Great. MLflow is also an open source software project that lets you track machine learning experiments. Basically, for the tracking of runs, we're building upon MLflow, so we're extending it in a way. You have quite a lot there already. This is the MLflow UI that I'm showing you right now. You can run this locally. We deployed it to the cloud to make it easier for you. And basically, you have experiments here. This is one thing we are mirroring with our user interface. And then each experiment contains several runs. And what you can see here is that there are different users. And this Seidler1, for example, is my username on Jules. So what you can do with our platform already is that you can automatically execute your projects on a supercomputer and track them to a cloud instance. So there's actually no need whatsoever to SSH on the supercomputer anymore. There's a bunch of nice features. For example, you can log models or other artifacts. You can even register models. You will be able to just use the stored models for inference. That is quite easy. So there's a ton of handy ideas, and I hope you will take a look at well, at the platform as it works so far. As I said, just give me, just hit me up for a trial account. I would be pleased. And also, I think you're in a very nice position here. I will be here the whole week, mainly as a student. But if you force me to, I will be here as a software developer as well. So any feedback whatsoever is appreciated. And if you have reasonable requests, it's quite likely that we will implement them. Thank you very much. I think we're a bit before time. I thought it would take longer.
We can go through questions.
Oh, yes, sure. Also, we can revisit the survey. Any questions?
We see some programming languages, but what's your main programming languages for data science? What do you recommend? Here we're discussing Python, R, and Julia.
So MLflow is mainly targeted on Python, and by transitivity, our platform as well, as it is now mainly targeted to Python code. But in principle, it would be possible to include other languages as well. But personally, I know Python quite well, and I don't know R or Julia. So I hope I get some introduction here and can answer the question better by the end of the week.
I have one more question. Well, Ben, have you considered in the KISTE project like automated benchmarking platforms like AutoML or something that you can just add a data set, a problem, and load all the existing solutions and do benchmarking quickly, including Kaggle and.
It's not targeted to benchmarking. It's kind of there might be benchmarks in it, and they're kind of the target is really more to kind of educate people to use it properly, to use machine learning properly. But you also have kind of code examples and snippets that you can reuse and possibly kind of use for benchmarking, but it's not meant as a benchmarking platform where you can see different solutions, different purposes.
Mm-hmm.
So,
and how much the interpretable machine learning then comes in? Do you have some diagnostic tools to see where the problems happen?
Not at the moment. So we are trying to be agile on this, and if this is a feedback we get that it is heavily wished for, then we will think of a way of including this. But at the moment, we are more focused on firstly all the bookkeeping, then automating execution on several compute backends, so HPC or cloud or wherever, and well, then we'll have to see. Would be interesting, surely. I think it might be possible with our idea of multi-step workflows, but I didn't go into detail because it would be too much for now. But basically, we want to modularize also the workflows. So
and the OpenGeoHub Cloud, is that system you would like to use, or to like register the processing flows?
It could be a nice addition, actually, so that we not only have the Unit computing cluster kind of standard cloud providers or the local solution, that you can kind of provide an OpenGeo driver, so that you can also connect to OpenGeo, which is kind of similar ideas at many points, kind of that you have your kind of code platform agnostic and you can send it to different cloud providers. This is kind of very similar to the ideas that we kind of try to make life easier in this AI platform to run different analysis in different infrastructures.
OpenGeo has also visual builder, I think, so you can connect just processes visually.
Yeah.
I mean, this it's quite challenging to do this visual connection thing properly and in all generality. This is why we are a bit hesitant.
I think it's better to make a code.
Yeah.
But they did make the visual editor, yeah, so you can connect the workflows and visually can connect stuff and objects and things.
you need very good metadata that you know that the outputs are suitable as inputs for the next process, and you have kind of figured that out and do all kind of matching if you want to do it properly. And that's kind of so far hinders us to really do it. But the idea is nice. So if you envision it that you have kind of different boxes you can just connect by arrows and doing links and connections, and you build up a new workflow. You take pre-trained models from somewhere, and you do some transfer learning and put in some new data and improve the model. It could very nicely go into the user interface, but there's kind of, I think it's a tough question on the back end to really have this properly done.
The models, I mean, you fill the model like in R, and you save it as RDS, let's say. But this model will only work with, compatible library, right? So how do you make that work?
Containerization, but this will happen in the back end. So basically, there's a certain structure that we impose on machine learning projects, which is quite simple, but at some point you need to define your requirements, and from this we build a Docker container on Apptainer container actually for running on HPC, and there will be a registry for those, and then you can run anywhere basically.
Marcus, you wanted to add to that?
Yeah, I want to comment. So the solution was containerization, and we, in the first version of this platform, we had a more complex backend. The first version of this platform, we had a more complex backend. We had more problems in the backend, and people were refusing to use it because it was too complex to use. But actually, we did exactly what you said. We sketched the different steps in the workflow. We could combine them, and you can at least reject things that don't match together because they have the wrong interfaces. So they are automatically indicated that this doesn't run, or yes, it runs. But in the very end, usage comes first. So if people don't use it and we die in beauty, it's not useful. So I think this is the second or third step. If we now see that these 40 people, 10 use the platform, and all of these 10 want to use this feature, then of course we will implement it.
That's another question.
Is it also possible to add documentation on how and why the models work, or is it only about more about the computation part?
Well, we have planned certain fields where you can add descriptions to the projects themselves, but also to experiments within the projects. So yes, descriptions are planned, but no automated explanations. So you will have to do it yourself still.
Is this platform specific to late Earth observation data? So I know I'm aware of some kind of frameworks for doing this type of workflow, say for like natural language processing. Is this platform kind of particularly targeted to like geo data?
Well, at the moment, technically no, but we certainly, since we are sponsored by the KISTE project and by another project that is also mainly focused on meteorology, we surely have this Earth observation data in mind when building it. So on the content level, yes, we will try to provide examples only from Earth observation. But as long as we don't have to, we will not restrict ourselves to this field. Oh, wow.
Do you want to show something else, maybe?
Well, then maybe let's really first revisit the survey, since we have it. Then do you want to take over quickly again?
Okay, let's jump back in here and see what we have as reasons to not kind of move to a larger region. Okay, it's still moving. So still somebody able to give feedback, and that's nice. So time seems to be kind of the more important here. It's getting growing larger and larger. That's interesting to see. So wondering, maybe we can kind of get that here as a response. Is it kind of your personal time to kind of prepare your code, or is it kind of computational time to move to different systems?
Second one for me, at least.
Second one for you, at least, yeah. Okay, so kind of bigger infrastructure could possibly narrow down kind of the time constraint, and then will make it be possible. Okay, that's interesting to hear. That's good. How is built? Depends privately. Well, privately is a problem. It's already a reproducible framework. That's very good. That's nice.
What does medium mean?
Well,
Reproducible?
Well, it's kind of halfway reproducible.
So 50% is reproducible?
Yeah, kind of, I guess. Yeah. But it's a quite open question. We could have put a kind of slider here to move it from non-reproducible to fully reproducible, but then still, I think we have to discuss that in the reproducibility hackathon, which will run tomorrow evening, where the idea actually really is that you bring your research that you have done and kind of put it here on screen and say, whoever's interested, kind of try to reproduce my research, and let's see how reproducible my research actually is. So that's kind of the idea of the reproducibility hackathon, but there will also introductory sessions and talks, as you see from the program tomorrow morning. So that's a kind of interesting question for us as kind of infrastructure data provider. So different databases, shapefiles, just R-based, Excel, my special friend, Throughout spatial in different terms. Okay. No one using OGC standards, apparently. Just us, seems like. Okay, good. I got that. Your favorite pre-processing tool? Flavors, yes. Variable selections. Principal components, nice overview. Main modeling approach, maximum likelihood, that's a favorite. So the random forest is very, very prominent here in the center. Tuning and repeating, yeah, I can imagine. Interesting to see. Okay, we didn't get any answers here, apparently. The question was too open. We have to narrow that down for the next time. Well, no and yes in some stages, but the yes is larger than the no. So apparently more people use the multi-step workflow than not using it.
Or people are more incentivized to answer if the answer is yes.
And the continuation question. Some from time, some rarely, some I haven't heard about it apparently. Okay, we can keep this open, and I will check if there's any limitation we hit and if we can make it kind of open it again, and I'll let you know over MetaMost at that point. Any further questions? Anything online coming up? Otherwise, we can take it in an agile manner and just kind of head on to the explanation how the research speed dating might work. Any objections? No? Okay.
Okay, so we start with KISTE speed dating.
So, well, repeating it, kind of try it out. Here are the links, and talk to Thomas if you want, if you need a test account for the Semantic platform. And then, yeah, next will be the research speed dating. I think we stopped broadcasting that because that doesn't make a lot of sense, right?
Yes, we stop.
Yeah, good.
But also on your side, you have to stop.
Yeah.
Das war ein Handy, so ein Chrome-Fenster.